Welcome to lesson 9.1. Let's take a look at this bell ringer. The number one problem says to determine the magnitude and direction of the resultant of a vector sum described by 16 meters to the north and then 25 meters west. So whenever we are using the system northeast, southwest, remember that north starts at the top of what would be your, come on now, XY axis, north, east, south, west. Never eat shredded wheat, never eat sour watermelon, whatever term you want to use. That's going to be the framework. This says there's going to be a resultant, which means it's going to have two or more vectors. The first one is 16 meters north. And they could have said due north. Due north just means it goes perfectly straight towards the north. So here, this is 16 meters due north. And then it's described as going 25 meters, I'm sorry, 25 meters to the west. Now, I want to remind you a couple things. I'm drawing this correctly here. Some incorrect drawings would be if you went back to the origin, said it like that, that would be incorrect. It would also be incorrect. So we're supposed to draw tip to tail, tip to tail, tip of one vector to the tail of another. It would also be incorrect to say, all right, well, my second vector has got to go due west, so it should point at the west. No, that would be incorrect. It's from this new location. West would become horizontal from this point. That would become the new west, if you will, kind of like that. So what does that mean about the resultant? Well, the resultant is the vector from the initial location to the new final location, which means this would be on a northwest path. It would go somewhat to the north and west, so it would be northwest. Let me label up here. This is 25 meters. And then this would be our resultant here in black. I'll just do R. So as we started going through this in chapter 8, I was drawing 4 vertical lines to help you keep track of your math, 4 vertical lines and 3 horizontal lines. This will actually create somewhat of a table that has, I know it's going to sound tricky here, I'm going to say 5 columns and 4 rows. You might be like, well, wait a minute, we just did a 4 by 3. That's true, but as far as cells are concerned, you have 1, 2, 3, 4, 5 for columns, 5 columns, and 1, 2, 3, 4 for rows. And I was labeling these. I'll write it out fully this first time. V for vector, X here for horizontal, Y in the next column, and this represents the vertical component. I was using the letter H. It might be wiser to use the letter R here. I'm going to use the letter R today because that's what you're going to see today. And this is the term magnitude. This is a U in there, it's shrunk. And then we have a theta. So the reason I put that in green is because I've been using the letter H because we think of it as a hypotenuse. But today we're going to see the letter R, so I'm going to keep it consistent for today and put an R there. Vector 1 was the 16 meters north, so I'll just put north in here to label it. And vector 2 will be the one that went west. Put that here in blue. And the resultant we drew in black, so I'll write that here, black resultant. Okay, so as it turns out for mathematics, the way this works is you would plug in your values. And by the way, if you have X and Y values, that's called a rectangular. It would be in rectangular form, or you could call it rectangular components. And then over here would be polar form. Okay, so back over here. I have a 16. And as I look at it, the question to ask yourself, and this is really the reason why I normally use the letter H, is I say, okay, does it look like an X value, something that's parallel to the X-axis, a Y value, something that's parallel to the Y-axis, or is it slanted and as the triangle is concerned, look like the hypotenuse piece? Well, the case is for the 16, it's my vertical component. It's going up and down. It's parallel to the Y-axis, so it would go in the Y column, the 16. Because we're moving up, it would be a positive 16. And every rectangular component needs to have its partner component. We have the vertical, so the horizontal would just be 0. We don't know about its magnitude or direction. I could fill this in. I actually know what it is. this is the same thing as by angle going 90 degrees. And so technically you could say that one piece would be 16, 90. Now you don't have to know that because you don't need that in this problem, but that would be the truth. Now when I go to the west, this piece over here, I look at it, it looks like the x component. It's not diagonal, so it's not the hypotenuse. It's not parallel to the y-axis. This would be the horizontal. And so it'd be 25 here with a 0 in that spot. Now, if I leave it like this, though, it's incorrect. Who can figure out what did I do wrong for the west? Negative 25, because it's going to the left. It needs to be a negative 25. Now, how would that work for polar if you were just dealing with this angle itself? Well, this would be from the positive x-axis, 180 degrees with a magnitude of 25. So again, you don't need to know this, but that's what the value would be here if you need to know polar. So I said this one was originally 16 at 90 degrees. That would be this piece. This one over here, it has a magnitude of 25 meters at 180 degrees. That's polar form. But again, you don't need to know those. Now we can get our solution, but if we use the calculator, I recommend calculator 24. Truthfully, I'm going to replace these symbols because you rarely see it in those symbols. Really, we fill out this table, so I'm going to do an image of that later. But this is calculator 24 is the one we're going to use here. So my first vector is in the rectangular columns. So I'll put in 0 and 16. Notice my picture lines up perfectly. My second vector is also in the rectangular column, so I'll go second rectangular. I get 25 and 0. When I view the picture, my picture is accurate. And if I slide down here, this calculator will calculate all 4 values across for the resultant. Now, this is neat for just the math rules here. The way it works is the x and y column combine together. If you have all of them listed, they would combine together. And that's why this is going to say negative 25. Let me come over here and shrink this so you can see both at the same time. Okay, so we'd have negative 25 in the x column. The y column is 16. Notice these values add straight together. Now, I don't know if you remember this, but I told you, not that you had to know this, but this was 1690. This was 25 and 180. The hypotenuse or the magnitude column does not work the same way. Notice this value is not 41, rather it's 29.7. 29.7 degrees. And the angle is 140 or 147.4. So there I did just using technology. And I want to work through a little bit of the algebra so you understand. Well, let me write the answer first. They want to know magnitude of the resultant. So the magnitude would be this value right there, the 29.7. And that would be meters, because that was our unit earlier. And the direction is 147.4 degrees. Now that picture is shown 147.4 is from the positive x-axis over. Very frequently though, if you are given an angle or you're giving the directions north, east, south, and west, your answer will not remain in that same form. Typically, if you're given something that starts, let me underline directions since we were finding those two. If you're given something with the terms north, west, east, or south, you're typically going to write it in quadrant varying form, which means you need to go from either the north towards the west and list that angle, or from the west to the north and list this angle. Either way, these two add up to 90 degrees because there's 90 between the north and the west. So how could I get this angle or this one? Well, it's simple if you just think about pure geometry. On a straight line, how many degrees are in a straight line? 180. So if you wanted this one, you take 180 and subtract the 147.4. That would give you this one. Or if you needed this angle, you could think about it going, okay, how many degrees are there in a right angle? 90. So if you took a 147 subtract 90, we should get this angle. So I'm going to do those two real quick. If I took that 147.4, that's this angle from here to here, and take away the 90 that are for the first quadrant. Take away those 90. I'm left over for this side having 57.4. So I could write my answer saying this from north towards the west would be 57.4 degrees. Or I could have said from the west to the north. And again, you could just take every straight line, there's 180 degrees. I could take 180 and subtract that. 180 minus 147.4, which is 32.6 degrees. This one's 32.6. So notice what I'm doing differently on these two is this is from the north going to the west. This is from the west going to the north. If you added those two up, it would give us a total of 90 because there should be 90 degrees between them. We'll just do that as a check. 32.6 plus 57.4 is 90 on the dot, so we did do that one correctly. Okay, so now, in case you're wondering, you might be thinking, what's the math, Mr. Voorhees? How did you know those two? You told me they weren't important, but how did you actually get those? And how would I get these values down here? Well, if you have all your x's, you would just add these. If you have all your y's, you add them. How do you get the magnitudes? You do Pythagorean Theorem. So here's the algebra. If you wanted to do the algebra, you take the Pythagorean Theorem of the x and the y. So over here, you'd have 0 squared plus 16 squared, and then take the square root. Since that's 0, it's going to end up remaining as a 16. Here, you take a negative 25, square it, a 0 squared, combine them, and take the square root. Again, since that's a 0, won't change. The negative will get canceled out when you square it, and that's why it became a positive 25. Over here, I would square the negative 25. And that would be 625. You'd square this. I think that's 256 maybe. You would add those two numbers together, take the square root, and that was the 29.7 value we got. That's where that comes from. If you're wondering about the angle, you do the inverse tangent. Inverse tangent of 16 over 0. That one's actually going to be undefined. Tangent, whoops, -1 of 16 over 0. Oh, the calculator gives me 90. I guess it's just programmed that way. Typically, you're not allowed to divide by 0, but that's 90 like I told you. And then the west, this will give me 0, but it's actually 180. 0 divided by -25. It's going to say 0, but because I'm going left, 0 is actually going to the right. So I'm going left, I would add 180. Anything on the left side with inverse tangent will not give you an answer on the left side of the graph. So anything that's supposed to be on the left, you would add 180. That's the rule. That's how I knew it was 180. Notice these two do not add up to give you that. You would again do the inverse tangent. Inverse tangent of 16 over -25. You would need to add the 180 because again, you're on the left side of the graph, and that is the exact angle we got there. So there's the algebra behind what the calculator does. So there's number 1, really slowly done. Let's check out number 2. It says find the component form and magnitude of the vector AB with an initial point, here A, and a terminal point of B. So here's the idea. If we graph this, you have a point that originates 4 units left, 1, 2, 3, and 4, and 9 up. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's point A, it's the initial point. And we have a terminal point, 7 to the right, and up 1 unit. 1, 2, 3, 4, 5, 6, 7, up 1. And so terminal to initial, or initial to terminal, starting to finish, would look like that. So when it says what's the component form, it's basically meaning how far does it move either to the right or left, and how far up or down. And so the way we learn this is you take your terminal points and you minus the initial, and you do this both for the x and the y. It's the terminal minus the initial. And so I'll take the terminal 7, that's the x, and subtract the initial x, which was -4. and I would take my terminal y and subtract the initial y. So here, a negative and a negative make a positive. So 7 plus 4 would be 11. 1 minus 9 is a negative 8. There's my component form. And like I was just saying a second ago, if you want to use the algebra, you do Pythagorean Theorem. The magnitude, I'm just going to write mag, will be 11, the square root of 11 squared plus negative 8 squared. So now let me show you, I did do this by calculator. We'll find out what that is. I think it's going to be a crazy decimal, so I'll do a squiggly here. I'm guessing, could be wrong. I'm going to use a different calculator here. I have one of these calculators here. It is calculator 25. It says initial and terminal. If you have those, open that up. The initial point we said was 4 to the left, 9 units up. The terminal point was 7 to the right and 1 unit up. So you can see this vector does go 11 units to the right, 4 there, 7 more, that's 11 to the right, and it traveled 8 units down, as shown right here. 11, negative 8, there's the component form. This asks for the magnitude, which I would get a square root of, or excuse me, about approximately 13.6 is our value there. Approximately 13.6 units would be the magnitude. What is that as a square root? 11 squared plus negative 8 squared. 185. Square root of 185 is that 13.6. Yep, so we did our math right. The square root of 185. All right, so there's your bell ringer. There was kind of an algebra overview as well as a technology usage. Let's take a look at chapter 9 now. So chapter 9 is when I'm supposed to, I say supposed to because I've been doing it differently, introduce polar. So you have some new vocabulary. A polar graph is going to appear differently. It's going to not appear like an X and Y axis, but it's going to appear as a graph kind of like this piece. Let me come back here now. You're not going to have a normal X and Y axis. That's how a polar graph is going to work. If you've seen a movie where there's like a submarine or a battleship or airplane and it has radar or sonar, you've seen something similar to this. And what happens is there will be little blips or little dots. They're placed in the screen in the movie, and they're able to determine how far away that either the enemy or opponent or whatever it is located, and not only how far away, but on what angle. This is polar. Okay, so that's the polar coordinate system there. A pole is like a straight line. So like, for example, here's the pole 120 degrees. It's that line all the way across. The pole 120 degrees would look like this, a line with arrows pointing both directions all the way across. That's a pole. The polar axis, let me switch colors. Polar axis is the pole that points at 0 degrees. That's the polar axis. That right there is the polar axis. And polar coordinates are going to be represented by an r and a theta. R theta. Okay, so I used R number 1. You might have been thinking, why did you switch from an H to an R? Well, because in the polar system, the R, we think of the letter R representing radius. And if you look, this is a whole bunch of circles. So let's say you had an R of 2. What that would mean is that the point would be on the circle that has a radius of 2 units. So if you went from the origin out 2 units, you're on the correct circle. And so a polar equation will be in the form R equals, it'll just be graphed on something similar to that. All right, with all of that, let's get started. So on number 1 here, it says graph point S. This is saying we have a magnitude, which equals 1, or you could say the radius, the circle with a radius of 1. It's going to be a point where theta is equal to 200 degrees. So I'm looking on this first circle at 200 degrees, which would be somewhere in between those two. So from the origin, it would be somewhere in here would be my point S right there. That would be the value of 1, 200. And I forgot to say this would be the direction. I didn't write that. Direction is 200 degrees. Just to give you a couple extra, let's just say we had the point A. If you wanted to have the point A, 3, 270, what that would mean is you would find 270 degrees and you go to the third circle. 1, 2, 3. That's 3 circles out. Or you could say the radius that happens to have, the circle that has a radius that's 3 units long. 1, 2, 3. This would be point A there. And if you wanted one more point just for good measure, just to make sure you really know what's going on, we could try 4, 45 degrees. You find the pole that's 45 degrees, and we go to the circle that happens to have a radius of 4 units. So 1, 2, 3, 4. This circle right there would have the radius of 4 units. I could label these 1, 2, 3, and 4.
Okay, so Morgan,
What's that?
I wasn't here because I was doing that.
All right. So let me show you one more now. So it says graph point R, and I want to throw in something. You might see some negatives. So how does this work? So a negative magnitude means you need to go the opposite direction. A negative magnitude. I don't know why I put a minus the negative. A negative magnitude. There we go. Magnitude means to move in the opposite direction or away from theta. So instead of moving 2 circles or a radius that's the circle has a radius of 2 going towards 3 pi over 2, we're going to move away from 3 pi over 2. So here's 3 pi over 2. So instead of moving 2 radiuses towards it, if you will, I want to move away from it. 1, 2. There's my magnitude. 2 units away from 3 pi over 2. So starting from the origin, I went away from it, and that would be point number R. Mathematically, this point R, you're going to learn in this lesson that we could write the points in 4 different ways. It's equivalent to saying this is on the circle with the radius of 2 at the angle pi over 2. So I want you to look at these 2 points here, R and R. They're identical to one another. It's the same point, but written 2 different ways. You'll actually learn there's 4 different ways we could write a point. You could do it reflecting across from here, and then we'll come into what if we had negative angles. So what do I mean by negative angles? So that's the point if your angle was pi over 2 going this way. What if we went around the circle going this way? Well, we'd have a negative theta. You'll learn that when you're dealing with a negative theta, instead of looking at the value it's actually on, you would look at the opposite value. Why? Because 3 pi over 2 going this way is the same distance as going around this direction. So I could also write, I'm getting ahead of myself, but I'm just going to tell you now, I could write this as on the second circle, but with the angle being a negative 3 pi over 2. That's how far around I went. There's negative 1 pi over 2. There's negative 1 pi. This would be negative 3 pi over 2. You can just see I'm reading the values backwards. And so that would be negative 3 pi over 2. And finally, the trickiest one. So again, I'm getting ahead of myself. You're about to see this later. But the trickiest one is if both values are negative. Both the magnitude and the angle is a negative. And so that would be the idea of, okay, I want a negative angle, but I also need to have a negative 2 across. So what would that do? That would look like instead of being up here, if I wanted to have a negative 2, that would mean I'm pointing at the value here. Now, again, we're dealing with negatives, everything's flipped, so it's going to be strange. It'll be negative 2, negative pi over 2. Now, you might be looking at that going, what in the world on the blue one? Well, we'll get to that one. The blue one's always the hardest. But The first three are a whole lot easier to find than the fourth. I do have a pattern for this, which I'll get to later. Okay, so anyways, every point can be listed 4 different ways. That's getting ahead of myself. Let's just work on plotting the first one. I'll give you the most basic. I want you to plot this point, 3, 120. Here's your problem, your choices, and here's, you can look at where the point should be located and then figure out which picture accurately depicts this from the textbook. DOL number 1. Now let's take a look, example 2. So now I'm just going to start throwing in more of these negative angles, which I kind of spilled on the last problem of how it's going to look. So I have here A at 3 with a negative 5 pi over 6. So that means instead of going with an angle around this direction, this would be the positive angle going this way. That's if theta is greater than 0. Instead, we're going to be looking this direction. So theta is less than 0. And so these angles are listed by the distance of, if you remember how all this works, it's the distance of how many measures of the radius around going this direction. So 5 pi over 6, instead of it being over here, 5 pi over 6, it's the same distance, but we move the opposite direction. So instead of moving this way into the last pole before pi, I would go this direction to the last pole before pi, which would be here, 7 pi over 6. So it's the third circle, or it's the circle with a radius of 3, I could say, will be where I plot point A, facing 7 pi over 6. So if there's 4 ways of writing every point, and they gave us this one, we just discovered that you could rewrite this as a radius of 3 on the pole 7 pi over 6. So these 2 points are exactly the same as one another, or represent the same point. So the negative 5 pi over 6 is going this direction. That's negative 5 pi over 6. It's the same distance as going around 5 pi over 6 this way, except I'm moving in the negative direction, downward. Okay, so what is that 7 pi over 6? 7 pi over 6 is if I moved around this way. Notice I went around the circle further. That's why it's a bigger number, 7 pi over 6. The negative is only indicating the direction at which it started off. So what about the other 2 values? Well, the other 2 values have to do with the reflection of the magnitude. The other 2 values, so the next one, which would be the next easiest, is to say, okay, what if I wanted to list this point but with a negative magnitude? That would mean I would talk about the pole that's facing the opposite direction. So instead of 7 pi over 6, if I went the opposite direction, it would kind of resemble this point here, which, though it's pointing at pi over 6, we'd say it has a radius of negative 2 at pi over 6. So what does that mean? That means find the angle pi over 6, but move away from it 2 units. So instead of going 2, excuse me, I put a 2. Why did I put a 2? It should be a 3. I move away from it 3 units. So instead of moving 1, 2, 3 towards pi over 6, you go away from it 1, 2, 3. And again, you end up at the same point. So all 3 of these are equal to one another. Now, the last one, I told you a second ago on example 1 that there's kind of a pattern to this. How would you find your last one? Well, the pattern, the easiest pattern to see is you could process of elimination some of this. You're always going to have 2 that are positive magnitudes and 2 that are negative. So this has to be a negative. And the angle's the same is true. 2 positive and 2 negative. So right now I have 1 negative and 2 positive. So that means my angle will be negative. The other value, this is a lot easier in radians, is that if these values are in pi over 6s, notice they're all pi over 6s, it's going to be the last remaining pi over 6 that I haven't used. So notice I've used 1 pi over 6. I've used 5 pi over 6 here. I know it was negative, but ignore the negatives for a second. I've used 7 pi over 6. I have not used 11 pi over 6. That's going to be my last one. So right here, I know we haven't gotten to it yet, but these 4 points are all equivalent to one another. As it turns out, the double negative will always appear to be a horizontal reflection. This is compared to this one. It's a horizontal reflection. I'm going to call this the original. And so everything here is going to be compared to this one, the original here. The one with the double negative will always appear to be a horizontal reflection. The double negative, meaning the magnitude and the direction are negative, it'll come from the angle that's reflected horizontally. The one that is just the magnitude negative will appear to be reflected diagonally. Reflect, I'm going to say across origin, which means it's diagonal. And the original negative, it will appear to be a vertical reflection. So from 5 pi over 6 to 7 pi over 6, it appears to be vertical. So this one will always appear to be, if it's just the angle, to be a vertical reflection. Now that's not mathematically the best way of doing it, but that is by appearance how they work. Okay, so I'll show you that a few more times. I'm not just going to show you this once. All right, so let's try to graph Q -2, -240. So you remember what I said about if it's a double negative? The double negative is always going to appear as a horizontal reflection. So what does that mean? If you find -2, or so if you find 240 as a positive, it'll appear to be a diagonal, or excuse me, a horizontal reflection. So instead of it being plotted here, it's not going to be plotted there. That's that point. Let me go blue to match it up. Not actually going to be plotted right there because they're double negative. It'll be the horizontal reflection. So this is the first pole after the y-axis of 270 here. So it'd be the first pole over here. That's actually going to be my point right there. It's very strange. It doesn't look like it should be there, but that's where Q will be placed. Now I've been kind of giving you the visual. On the next example 3, I'll give you the algebra that's required. So what's a better way of writing point Q? There's a better way we could write point Q using only positive numbers. What radius would we give it? Radius of 2. And what pole is it located on? That would be if you were going away from 120. Right now it's going towards 300. So this would be the best way of writing it using only positive numbers. That's what I would call the original. I would label it that way. Okay, the next easiest way would be to say, what if we just went a negative magnitude? A negative magnitude would be the one where you go away from it. So like this spot right here, if I thought of it this way, that would be 2 circles away from 120. So radius of -2 at the angle 120. So notice what I said that on the previous slide, I'll show you in a second, that if you only have a negative magnitude, it appears to be a diagonal reflection. So a negative on the magnitude, here it is. It appears to be a diagonal. It's reflecting across the origin. The origin is hard to read. What is that? It says origin. Write that clear. Origin. There we go. And so one more. We have the double positive. We have the double negative. We have the positive, or excuse me, another negative. Let me switch colors. We are missing, you need to have 2 of each, a positive length, positive magnitude, and a negative angle. If you're like, where is that angle? Well, if you look at it, you should have all 4 pairs being used. It's a little bit harder without radians because you can't just look at the denominators, but I can see that I've used 300 and 120 there on the same pole. I have used 240. I have not used the 60. So it'll be -60. 2 at -60. This one appears to be a vertical reflection. When it's only a negative on the angle, it appears to be a vertical reflection. So that's how you would list those. All 4 of these Q's apply to this one point there. These other 3 are just that are plotted there. Those are not the real point. Those are just kind of like placeholders to allow you to see how they're related to one another. Okay, I want you to find just the one point. And you know what? I didn't even tell you yet. I've got a calculator for this. Oh my goodness. Do you really? Yes, I do. If you go to your calculator list, it's calculator 28, plotting polar and rectangular coordinates. If you open this one up, the problems we just did, like -2, 240. If I plot that in, it's -2 and 240. I think it was -240 actually. So the -2, -240. Yeah, -2, -240. If you plot that, you'll see the point is shown down on the circle with a radius 2, so the second circle on the pole of 300 degrees, just like we had here. So you could use that for this problem here. Just make sure you change your mode to radians if you're going to use it on DOL number 2 here. And this one's in radians, so you'll need to switch your mode by going to the settings in the top right. Let's take a look at example 3. It says find 4 different pairs of polar coordinates that name point S. Okay, so this is exactly what I've been doing, but now I'll show you the algebra. So here's how it will actually look for you. Almost your homework is you'll have this system where you have to label the first point. So none of the 4 are given to you. So the first one is on the second, or it's on the second circle, or I could say the radius that has a length of 2, circle with a radius, a length of 2. So point S has a length of 2, we know that. Whoops. The radius is length 2, and it's on the pole 210 degrees. Now I'm going to write out the 4, and then I'm going to give you the algebra that goes from one to the other. So as a reminder, once you find 1, the other 4 are going to be appearing to be like a kind of like a box around each other, a pure rectangle. And so the easiest one I think to find after you found the double positive is the one with a negative magnitude. So it's the pole directly across, which is 30 degrees. So it's the pole that's 30 degrees. But because I'm not heading towards 30, I'm going away from it, I would label it as a -2. So I'm finding that point now. Let's say -2. Now I'll switch colors. Now, what if, so let me say this. This point right here, the first time we said that was 210 degrees going this way. What if I went around this direction? This is saying I have a negative angle. Well, as you can see, what I've done here in red is a total 360. So what is the opposite of 210 is 150. So if I came this way, it'd be negative 150 degrees. Okay, this would be that vertical reflection I was talking about. From right there down, it looks like a vertical reflection on the 150. But now you can kind of see it that these two should add up to 360 if you ignore the negative. The negative just means you're going downward. 210 plus 150 or 360. And so this one would be 2, it's negative 150 because I'm going downward. Which brings us to our fourth point. The fourth one we're missing. If I said they kind of make like a little rectangle if you put the others as placeholders. So the 30 degrees, 150. The other one would be over here. So since this is 30 past 0, this would be 30 under. It will be the 330. It'll be at 330. And here's the rule. You always have 2 magnitudes that are positive, 2 that are negative. So this needs to be a negative. And the same with the angles. 2 positive, 2 negative. This is going to be a negative. So I filled that out using just kind of some visual cues. Now, what's the math relationship? And it's this. If you think about driving a car, you're driving, let's say north, and you bust a 180. If you do a 180, what does that mean you've done? It means we switched directions. Wasn't a straight line there, but it means you switch directions. Well, polar is the same idea. Notice between 210 and 180, what's happened is I've subtracted 180 degrees. If you subtract 180 degrees, you have to change your direction. So instead of moving a positive direction, we're now moving a negative direction. Well, then between these two, I bust another 180. If you do another 180, that's subtracting 180 from 30 to negative 150. I subtract 180. Again, I change directions, and so it goes back positive. And so now you'll see on this very last one that if I subtract 180 one more time, my direction changes. So from a positive magnitude of 2, it goes to a negative magnitude of 2. And I go from negative 150 to negative 330. I know when you look at it in this form, this method looks easier. But not always does it actually turn out to be that way in practicality. So I'm kind of showing you both methods, but that's the algebra. Every time you do a 180, notice your direction changes. These also change from positive to negative, positive to negative. So this is example 3A. I'll have another one for you. Let's now look at it in radians. All right, point T, the easiest way to list point T is to say it's on the circle with a radius of 4 on the direction or the pole pi over 6. So T will equal 4 and then pi over 6. Now, if you want to try using the algebra, what you would do, like what we did the previous, is we would subtract, instead of 180, you have pi over here sitting as 180. So really what I'm going to do is subtract a pi. Because we're dealing with a fraction, you need to subtract using a common denominator, which means I'm subtracting 6 pi's over 6. That's really what I'm subtracting each time. So the next point, whenever I subtract this, notice your direction should change. It should be a negative 4. And I subtract 6 pi. So I have 1 pi over 6, and I subtract 6 pi's over 6. 1 pi over 6 minus 6 pi's over 6 is a negative 5 pi's over 6. Notice that my direction changed. Now, truthfully, all 4 of these t's are in the same spot, so you don't have to do that. If you're doing the algebra, you don't have to do those x's or whatever to visually help you get all your answers. So I'm not going to do that this time. So, okay, let's try the next one. Again, I would subtract 1 pi, which means I'm subtracting, let me just write it one time this time so we're not as confused. I'm subtracting 6 pi's over 6. I'm doing this because it's a fraction. I need a common denominator here to subtract. So the next point, my magnitude is going to go from negative to positive 4. Negative 5 pi over 6. And I subtract 6 pi over 6 is going to give me a negative 11 pi over 6. So now I got my third. Now you might be sitting there going, Mr. Voorhees, this is definitely easier. Why didn't you show us this first? Well, because you run into a problem here. If you try to subtract 6 pi over 6, we break a rule. This would be negative 17 pi's over 6. What rule did I break on this fourth point? Look at the angles in particular. That's where I broke the rule. There's 3 negatives. How many negatives are you supposed to have? 2. This is not within the domain. This right here is outside the domain. Negative 17 pi over 6 is less than negative 2 pi. It's outside domain. So that one won't work. So what do you have to do in that situation? Well, we'd go back to the top, and instead of subtracting at the start, I need to add 1. So I'm going to add a 6 pi over 6 to get my last answer. So my last answer should actually be, again, I go from here now, will be negative 4. And if I add 6 pi over 6, it'll be 7 pi over 6. So visually now, I'll come over to my graph and I'll show you visually all the points. This one right here says you look at 7 pi over 6. So I'm looking at 7 pi over 6 in the fourth circle, but you don't move to it, you move away from it. And so that's why I would move away from it this way. And that's why I would be pointing at T. So there's that point. That would be the purple one. Let's see, we already did the black right there. Red. The double negatives always appear as a horizontal reflection. So that means it's referring to this pi over 6. That would be the red. Whoops, not a dot. Let me do an X. That's where that one would be reflecting. So the negative 5 pi over 6 means you go down to here and then reflect across. Or reflect across this way, sorry. And the green, that would be the placeholder that's on 11 pi over 6 right here. If it's only the angle, it's going to appear as a vertical reflection. If it's only the magnitude, it's going to look like a diagonal reflection across the origin. If it's a double negative, it looks like a horizontal reflection. That's how the reflections actually work. All right, so whichever way is easier for you, you can go for it. Here's your DOL number 3. I have your answer choices listed down here. I think if you just find, if you look at only the first point here that are listed, if you want to use the calculator, you should be able to get to your answer. But if you want to try using algebra, go from here and work around. Notice that this is on the radius of 7. They count by 2s. So this would have a radius of 7 on this one. If you want to use algebra. DOL number 3. You can use the guess and check technique using the calculator by checking values. If you plug in this one and this one and this one and this one, just see which one plots in the right spot. And whichever one's correct, all 4 answer choices should be represented by that point W there. If you use my Desmos calculator, the plotting one. Example 4 now. On example 4, it says graph the polar equation. So we're finally getting to polar equations. And I'm going to stick very basic today with only showing you 2 different shapes. One is if they give you an r without the theta. So remember, polar, we typically have an r and a theta. You've seen it like this, symbols before. If they only give you an r, what it means is the theta does not matter. This is true for all thetas. You have a radius of 2.5. So that means, let me show you by looking at a vector. If you have a radius of 2.5 or a magnitude of 2.5, what it's saying is it doesn't matter what the theta is, you always have a magnitude of 2.5. So said another way, it's a circle. It's a circle that happens to have a magnitude of 2.5 or a radius of 2.5, just like that. That would be the graph of r equals 2.5. Could you graph this in Desmos? Yes, very easily. Let me just get a blank graph to show you. R equals 2.5. It's a circle. And by the way, if you hit the little graph settings over here in the top right, the grid, that second option is how you switch over to polar, by the way. Just so you know. You can see it is a circle with a radius of 2.5. There's 5 there, so that means it's 1, 2, 2.5. All right, so what happens though if it's just the theta? So this time you're missing the r. So again, polar, it's supposed to have an r and a theta. What if you don't have an r? That means it doesn't matter what the radius is. It doesn't matter what the magnitude is. It's always going to have an angle of 5 pi over 6. So here's how students mess this up, is they might think, well, it doesn't matter what the radius is. The radius could be 1, maybe it could be 2, maybe it could be 2.5, maybe it could be 3, anything right there, which is true. But don't forget, you could also have negative radiuses. It could be a radius, so with the angle of 5 pi over 6, it could be a radius of -1, -2, -3, -4, and so on. So it's actually a straight line all the way across, which means graphically, theta equals 5 pi over 6 will resemble the same graph as if it were 11 pi over 6. Those 2 graphs would look exactly the same because they're across the pole from one another. So anytime you're graphing theta equals something, that's just graphing the pole all the way across. You know, I did not show you earlier. How would you convert this? If you're like, how would you get this? What's the algebra behind this? Well, r, by rule, r equals the square root of x squared plus y squared. And so you could substitute that in here. The square root of x squared plus y squared would equal 2.5. Here's the math behind the graph here. If you squared both sides, that is going to be 6.25. So x squared plus y squared is 6.25, and that is a circle because you have both your x squared and y squared, and it's the same value over here. If you divide it across, it's not an ellipse, they had the same denominator, it's a circle. So if I graph that, x squared plus y squared equals 6.25. You see it's the same equation there, the same graph. It is the equation of a circle. That's the method behind that. If you wanted to graph this one, if you're like, how would I graph that? Well, it's a trick here. You need to take the tangent. If I said tangent theta equals tangent of 5 pi over 6, I'm going to come over here to the unit circle. Remember, sine is y, cosine's x, tangent is y over x. I'm going to order, send to back. Okay, if I'm looking at 5 pi over 6, here's my 5 pi over 6. The y is 1, the x is negative square root of 3. Those are the hypotenuse there. So on this, if you can see my writing, tangent theta equals tangent 5 pi over 6. That would give us, and right over here, tangent theta equals tangent 5 pi over 6 is 1 over square root 3. Negative square root 3, sorry. And tangent theta is the same thing as y over x. So y over x equals 1 over negative square root 3. If I multiply my x across, y equals, and I'm going to rationalize my denominator, negative square root of 3 over 3x. That would be my equation. Y equals negative square root of 3 divided by 3 times x. There's my equation. So not that you ever have to do that, but that's the algebra to get the graph. Right there. There would be the algebra to get the graph. All right, with that, I'm going to let you discover which graph is true for theta equals 7 pi over 4. DOL number 4. Now let's talk about polar distance. What that means is you have 2 points and you want to know the distance between them, and their points are given in polar form. Well, they give us this formula, and this formula is basically one we learned earlier this year. It is an application of the formula from the law of cosines. So earlier in the school year, in chapter 4, I think lesson 7, I gave you 3 formulas for the law of cosines. I'm just going to give you the first one, which said that a squared equals b squared plus c squared minus 2bc times the cosine of angle A. Well, here's what they do to get this polar distance. They say, well, the distance equals all of this square root. Well, where did that come from? Well, what they did is they said, okay, let's call A a distance. If I wanted to isolate the A, I would need to take the square root of all of this. And so I'd be left with A equals b squared, square root, plus c squared minus 2bc times the cosine of angle A. Okay, so where did I get all that? Why is it so much shorter? I'm not sure, but it is. Where did that come from? Well, if you look at it this way, as a triangle, that's an ugly line. As a triangle, that's still really up. Let me just use a triangle or a tool here. Draw a straighter line. This R1 distance is the distance right there. That's R1. That's R1. And this distance over here is your R2. What we're trying to find, according to the law of cosines, is the third side of a triangle. So instead of a B and a C, they would still call this one here, they'll call it A. So that distance would be A, this would be B, this would be C. Notice B is in the place of R1, C is in the place of R2. So I could say here B equals R1, C equals R2. So you can see it's like a triangle there. And now what about this theta here? How come this has just cosine A and this is theta 2 minus theta 1? Well, That's because what they do is they take the angle from here to here, and that's theta 2, and they subtract the angle that's from here to here, which is theta 1. But by the way, with cosines, it doesn't matter if you have a positive angle or a negative, they'll always be the same value. So if you subtract this angle from this angle, or vice versa, if you take this angle and subtract it from that angle, what you're left with is the angle in between these two spots, this portion of the angle from there to there, which means you would be missing angle A. And so true as it is, that is the law of cosines. Now, because that's a lot to type in, I did create a calculator for you for this. So if you go to your Desmos list, this one is your very last graph. Number 30, the distance between polar points. I'll open that up. We'll use that one after I plot the points. So here it says an aircraft controller is tracking two airplanes that are flying at the same altitude. The coordinates of the planes are for point A is a magnitude of 8 on a direction of 60 degrees, and B is magnitude of 4 on a direction of 300 degrees, where the directed distance is measured in miles. Sketch the graph of the situation and find its distance between the aircraft. So since they're counting as high as 8 by magnitude, I better count by 2. So 2, 4, 6, and 8. Point A is on the pole 60 degrees up at 8. So 2, 4, 6, 8. There's 8 at 60 degrees. And then point B was magnitude of 4 at 300. So here's 300, magnitude of 4. So 2, 4. Make sure you're counting by 2s. So there's point B. We want to know what's the distance between these two aircraft. And I'll use my calculator to help me out here. While I type it in, I want to tell you something very cool about this. If you do this for a living, the government sets regulations how many hours a week you can actually work, because they don't want anybody falling asleep on the job and allowing planes to crash into one another. So they don't even let you work 40 hours a week. And these people make a lot of money to do this, somewhat like over 100 grand. I might timestamp this because who knows with inflation whether 100 grand will be a lot of money in years to come or whether it won't be. But right now it's a lot of money, and they get paid a lot of money working less than 40 hours a week, just making sure planes don't crash into each other, because if they do, people die. It's a very important job. What this calculator does is it models, imagine that you're in the air traffic controller tower. I'm sorry, those big towers at the airport. You would have a radar and you would be seeing these 2 points. What you need to calculate is what's the distance between them. Make sure there's enough distance they won't crash. And the answer here is, oh, it's up at the top. There it is. Approximately 10.6 miles. The distance would equal 10.6 miles. Now, how did I get 10.6? What would be the math if you try to do this on your own? Is you would say the distance would equal the square root of 8 squared plus 4 squared minus 2 times 8 times 4 times the cosine of, you just subtract the two angles, 300 minus 60 degrees. So it'd be like cosine 240 there. And we found out that this is approximately 10.6 miles. They said in the problem that's measured in miles, so that's why I put the miles on there. That'd be the distance. All right, now I have one for you to try. Let's take a look here at how our ACP released questions have looked in the past. So these are just kind of ideas or models of what you might see in the test. It says, what are the polar coordinates of this point? Well, you might be thinking, so is this one where I need to transfer the point? Well, when you look at it, they don't appear to be the same at all. But not only that, this point is what we call rectangular form. Now, it's rectangular, and you might be thinking, how do you know that? Well, I can explain it quite simple when I say, look at the second value. If it had a degree symbol, then it would be a polar with a theta. It doesn't have a degree symbol. Well, or if it had a pi, that would represent radians and it would be in polar, but it doesn't. That must be an x and a y. So they've given me from the chart, if you think about it, an x and a y. So this first value here will be the r, which means you would just take the Pythagorean theorem if you're doing this algebraically, and this you would take the inverse tangent. But if it's on the second quadrant, remember how I said this earlier today, the calculator will not find an answer that's on the left side of the graph for inverse tangent. So on this point, I know that it's supposed to be 7 to the left and then up a weird amount like that. So it'll be the inverse tangent plus 180. To get this correct, you'd have to take the inverse tangent and actually not plus 180, it's in radians, so you need to add pi. That would be the math calculation to get the angle. But I'm just going to use my calculator. I'm going to use that same one that we used earlier for plotting points, which I don't know what happened to it, so I'll just open it up again. Plotting polar and rectangular coordinates. That's what this says to do anyways. It says, what are the polar coordinates? So I'm clicking on this one. They gave us two rectangulars. They gave us -7 as the x and 7 square root of 3, 7 square root of 3. There's my point. If you look on the circle, it's on the 14th circle. It says 120. If I change it here, go to settings and go to radians, it's on 2 pi over 3, the pole 2 pi over 3. So it's on the 14th circle. So a magnitude of 14 with a pole 2 pi over 3. So 14, 2 pi over 3, that looks like it's F is the correct answer here. And now the second one, which graph correctly represents the polar coordinates? -3, 2, 40. Okay, so this one we just match up picture. Again, we could use this calculator. Let me get the rectangular one off of there. -3, sorry, -3, 2, 40. My calculator appears to have frozen. There we go. But I need to change, this is now in radians, I need to change it back to degrees. So I go to that setting there. It plots it in the first quadrant on 60 degrees. So the answer choice should be J. If you're thinking, why is that? Well, let's think if you have a negative magnitude, that means you go away from 240. So if you found 240, here it is, you go 3 away from it. So I wouldn't go towards 240, I would go away from it, which would imply that that point is correct.